There's often a lot of stuff going on in a chemical reaction. You might have lots of different entities dissolved in a solution. Only some of them are going to actually react with each other and chemically change. And often as chemists, those are the ones that we care about, right? We care about the things that have chemically changed over the course of a reaction. Other things we don't care about if they're just kind of sitting there. So in order to drill down to just the parts of a chemical reaction that are reacting, we need to create a net ionic equation. A net ionic equation is going to show just the entities that are actually chemically reacting in a chemical equation. We'll consider chemical reactions that are taking place in solution here. And that's partly because lots of chemical reactions do take place in solution. And they can do that because as entities dissolve in water or in some other type of solvent, they can dissociate. Ionic compounds can dissociate from one another, and then they can react more easily with other things that are also dissolved in that solution. So it helps things to collide with each other. It helps molecules and elements to collide with each other. And when they do that, then they can chemically react. So we have to remember, first of all, what types of things will actually dissociate. So we're looking for high solubility ionic compounds. They're going to dissociate, come apart from one another. And so things like this silver nitrate. So we might remember from earlier on in chemistry, we showed dissociation equations. And those are when we take a high solubility ionic compound, meaning that it'll be aqueous in solution, and we show it coming apart. So this thing is going to come apart into the two ions that make it up. There'll be silver ions, Ag+, and there'll be nitrate ions, NO3-, and they're both aqueous. Because when the silver nitrate actually dissolves in the solution, it dissociates, it comes apart into the two ions that make it up, the silver ions and the nitrate ions. So what's actually floating around in here isn't silver nitrate all coming together. It's silver ions and nitrate ions, right? If we actually zoomed in and looked in the beaker, we would see some silver ions floating around, and we would also see nitrate ions floating around, and they wouldn't be coming together. They wouldn't be kind of traveling as a group. They would be separate from one another. Same thing is going to be true for this, because this potassium chloride is also aqueous. So it's going to come apart into potassium ions and chloride ions. And so in this beaker too, there would be also potassium ions floating around and chloride ions floating around. And then as it reacts, will form this potassium nitrate. Those guys will be aqueous too, but then it's the silver chloride that's now different, because the silver chloride is going to form a solid precipitate. And the solid precipitate isn't going to be floating around freely in the solution, because the silver is clinging tightly to those chlorides and they're forming a solid. So there would be a pile of stuff, precipitate, at the bottom of this beaker, and that precipitate would be solid silver chloride. And so what we might see is that if we're looking at this chemical reaction that we have written out here, this isn't actually the best way to represent, for our purposes, what's happening, because it's showing things that are together, but they're not really together. They're apart. And some things, like the potassium here, the potassium is going to be dissociated into ions before and after. And so if you look at the potassium, it hasn't actually changed. Started out as potassium ions that are aqueous, it ended up as potassium ions that are aqueous. It hasn't changed from the reactant side to the product side. Same thing for our nitrate. The nitrate hasn't changed from the reactant side to the product side. And so for both of those entities, they're not actually changing. They are what we call spectators, because the spectators don't change. They're like spectators in a sports game, right? The spectators in a sports game don't actually participate in the sport. They're just kind of hanging around on the periphery. That's what's happening with our spectators here. So the potassium ions and the nitrate ions in this case are spectators. The silver ions, the silver and the chloride, are not spectators, because they started out as aqueous ions and they ended up as solid So their state has changed. They're not aqueous anymore. Now they're solid. So those guys have changed. So the net ionic equation is going to help us drill down and look at just the things that are changing. So that'll be the silver ions, the chloride ions turning into silver chloride, and we'll be ignoring these spectators. So there are three things that we'll look at. We'll start with the non-equation. This is just our regular balanced chemical equation like you would have done in your basic chemistry class when you were just starting out. This is just your regular balanced equation. So this is the one that we were looking at here. Then what we'll do next is we'll write out the total equation. Here, anything that is high solubility is going to get dissociated into ions to show what would actually be existing in the solution, what would actually be floating around. And then we'll find the spectators, we will cross them out, we'll remove the spectators, and we'll be left with the net ionic equation, which just shows the entities which have actually reacted. So I'll show you how to do these steps for this first example here. So my silver nitrate, this thing is high solubility, it's aqueous. So because of that, it's going to come apart. So in the total, we'll actually have silver ions and nitrate ions floating around. They'll both be aqueous, right? The nitrate doesn't come apart like this polyatomic ion doesn't separate. It's bonded together covalently. That's a strong bond. But the nitrate comes apart from the silver. This potassium chloride is aqueous too, so it comes apart also into potassium ions and chloride ions. So it comes apart, it dissociates. Then on the product side, this guy, my silver chloride, is a solid, so it does not dissociate. No dissociation. It stays together. So in the total, you copy it down just as it is. Anything that is an ionic solid, anything that's in its elemental state, anything that is just a neutral element, it goes down here just as it is because it doesn't dissociate. If you had a molecular compound, it would also come down here. It wouldn't dissociate. Then here's my second product. This guy is aqueous, so the potassium nitrate does dissociate. Comes apart into potassium ions and nitrate ions, which are both aqueous. Then, now here's my total. Now, to build my net, I need to find my spectators. So I'm looking for things where two things stay the same. The charge stays the same. So the charge can't change, and the state of matter stays the same. If both of those things stay the same, then my entity is a spectator, and we're going to cross it out. So let's look at my silver first. It started out as aqueous, ended up as solid, so it is not a spectator. State of matter changed, even though the charge didn't. The nitrate started out as nitrate ions that are aqueous. It ended up as nitrate ions that are aqueous, so it's a spectator. We can cross it out. My potassium ions started out as aqueous ions. They ended up as aqueous ions. They are a spectator too, so we can cross them out. And my chloride started out as aqueous ions. It ended up as solid ions as part of this crystal lattice, so it did change. So my nitrate and my potassium were my spectators. So they're not going to get copied down into the net. We're just going to copy down everything that's left over here. So my net ionic equation then is going to be my silver ions plus my chloride ions, giving me silver chloride. And so then this would be my net ionic equation here. Let's try another example here. So in this case, I've got copper metal that's added to aqueous silver nitrate. It's going to react and turn into something. So we have to remember how to predict a reaction, and that's a skill from your first science class, from Science 10. And so what we need to do is first of all recognize what we have and what kind of reaction this is. So I have some copper metal. I know that that's Cu, and that comes as a solid. Then I have aqueous silver nitrate. Now, if I didn't know what silver nitrate was, now is when I'd go to my periodic table. So let's find these guys. Silver is down here. Periodic table tells us that silver has a 1+ charge. We're going to need that information. And we find nitrate over here is NO3 minus with a 1 minus charge. So just remember, when you're building this ionic compound, you need to have the same amount of positive and negative stuff in the ionic compound. The charges have to balance. So if you have a silver positive, NO3 minus, they'll come together. You only need 1 and 1, so it'll be AgNO3. And there's a separate video on predicting these reactions if you need to go back to that. Now, let's figure out what the reaction is going to be first of all. So we need our regular non. So we have the copper metal reacting with silver nitrate. And we're being told that that's high solubility aqueous. Then this is going to be a single replacement. So the copper and the silver are going to swap. Silver will end up as an element by itself, and copper will end up with this nitrate. Now, when the copper and the nitrate end up together, I need to figure out how many of each I'm going to have. So let's go back to my periodic table here. And let's find copper. So copper can exist as a 2+ or a 1+ charge. Now, which one do I use? Well, remember, if you don't know, in this case we don't know, then we choose the most common, which is the one that's listed first. So copper will form the 2+ ion because that's the most common. Nitrate still has a 1- charge. So we've got 2 pluses and 1-. So we've got 2 pluses and 1-. So we need 2 of these nitrates to balance out with my copper. So I'll have 1 copper and then 2 nitrates. Now here's an ionic compound. I don't know what its state is going to be, so I need to go back to my solubility table. So here's my solubility table. I'm looking up copper nitrate. Remember, you typically look up the anion, the negative ion first. So here's nitrate. And then I look down in these boxes and I'm going to see, where does copper come. So my copper could be down in this box here, but I don't see this. There's no copper nitrate there, so copper must be part of most. Then that means that copper and nitrate are going to be very soluble, so they'll form an aqueous solution when added to water. So my copper nitrate is going to be aqueous. Then the last thing we don't want to forget is we have to balance this thing. So I've got 1 copper, 1 copper, 1 silver, 1 silver, 1 nitrate, 2 nitrates. So I need to balance this guy with a 2, and then that's going to throw off my silvers. I've got 2 silvers here now, so I need 2 here. Okay, so I've got my balanced chemical equation. Don't forget to balance it. Don't forget to include states. You need both of those pieces of information. Now for the total, let's separate my ionic compounds that are high solubility. Remember, anything that is in its elemental state appears in just the same way. For some reason, when people are learning this, as they bring this copper down here, they like to give it a charge. They say, oh, I've been making things into ions, so I should give this guy a 2+ charge. It does not have a charge because this copper is in its elemental state. It is neutral. We give this next guy a charge. These silver ions get a charge because they are ions. We just don't show the charge when it's written like this as part of an ionic compound. But these silvers are silver 1+ ions. So elemental things, no charge. But things which are part of ionic compounds, this guy is an ion already, so it does have a charge. Now, what about my balancing? So this means that there are 2 silver nitrates for every 1 copper. So I need to include this 2, this coefficient in front here, to show that there would be 2 of those silver ions. And there are also 2 nitrates. So the 2 applies to the nitrate too. So when I write the nitrate down now, the 2 has got to go in front of that as well. Now on the product side, these silvers, they're in their elemental state, so they don't get a charge, just like the copper on the reactant side. My copper nitrate here, though, it is high solubility. It's an ionic compound, so it's going to get written as such. We're going to split it apart. These copper ions have a 2+ charge. They are aqueous. And these nitrates. Now, there are 2 nitrates for every copper, but they're not going to go buddy-buddy and stick together. This 2 doesn't mean that they stick together when they dissociate. So we don't leave it as a subscript. The 2 is going to come out as a coefficient. There'll be 2 nitrates floating around in the solution like this. Okay, so anytime you have a subscript, it comes out as a coefficient in front of the number. And you're going to see that anytime you have an ionic compound like this that needed to be balanced as such. So now I look for my spectators. Remember, the charge has to stay the same and the state of matter has to stay the same. If both of those things stay the same, then it's a spectator. Let's look at my copper. Started out as a neutral solid, ended up as an aqueous ion, so it definitely changed. It's not a spectator. Silver started out as an aqueous ion, ended up as a neutral solid, so it changed too. The nitrate started out as an aqueous ion and ended up as an aqueous ion, so there's my spectator. Get rid of that guy. I can rewrite what's left. That's my net equation. So the copper plus 2 silvers reacts to give 2 neutral silvers plus copper 2 plus ions. And so here's my net ionic equation. If you want to be extra sure that this is correct, there are a couple things you can check. The net charge on the reactant side should be the same as the net charge over here. So this thing was neutral. There are 2 1 pluses. So overall, this is 2 plus. These things were neutral. This thing is 2 plus. So overall, this is 2 plus here. So my charge should balance. It's not going to be neutral necessarily, but the charge should balance. And the other thing that should still balance is all of my elements. I've got 1 copper, 1 copper, 2 silvers, 2 silvers. If I did my balancing right up here and I properly carried it down into a total, that will be true there as well.